This is part 15 of the series Applications of Differentiation. In the next few lessons, we're going to look at a very common technique for the application of differentiation involving optimization. If you were working with more than one quantity that can change but are related, you would want to find the optimum mix. So it could be used to find a minimum of material, maximization of area involved or volume. So we're going to work on several different examples that explore this idea of optimization. In the first problem, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. We want to find the dimensions that will produce a box with maximum volume. Now, I'm a very visual person, so I generally like to create some sort of a visualization of the idea involved here. So I'm going to bring up my rendition of a picture representing this situation. So here I have a box, and the box is open-ended. You can see that there's no hidden line removal here. So the box has got an open top, and we know that our surface area is going to be 108 square inches. So we'll put that down, and we want to find, we know that this box is square base, so I'm going to create the variables x here representing the side length, and we don't know what the height's going to be, so I'm going to just make that h. So h is the height of the box, and we have a square base. So what we have to do is figure out what equations we're going to be able to work with to perform this maximization. Now, the problem details give us some of that information. We're going to be maximizing volume. So obviously we're going to need some equation that generates the volume of this box. So I'm going to put that up here. So volume is, and the volume is length times width times height. So what we have here is x squared h. So the volume is x squared h. We also have an equation for surface area. And surface area of a box, of this box, is going to be the area of all the faces. So I have x times h, and since this is a square base, I'm going to have x times h times 4, so 4x h, and I also have to include the surface area of this base here, which is plus x squared. Now, at this point, you may even be wondering why I'm even bothering with these equations. Well, let's go back and take a look at what it is we're trying to accomplish. We're trying to find the maximum volume. Well, think about what maximum is talking about. That's an extreme value. Maximums and minimums are extrema. And when we're dealing with extrema, we're dealing with differentiation. So we're going to be differentiating some function. And characteristically, in this problem, that's going to be the volume function. Now, we can see here that we have a volume function in terms of two variables, x and h. And I could implicitly differentiate this if I wanted to, but that makes things really ugly and nasty, and we're not interested in how one of these variables is changing with the other. What we're interested in is finding the change in volume that's maximum. So I would like to ideally get one equation in terms of one variable. Well, since I have two equations in terms of x and h, the most logical thing to do would be to come down to this surface area equation, solve this equation for one of our variables, substitute that result in here, and differentiate that result into that equation. So that's what we're actually going to do now. I'm going to go ahead and put in our values, solve this for h, and so I'll have an equation in terms of x and h that I can substitute in for this h, and everything will be in terms of x. So let's go ahead and do that. Let's give ourselves a little bit of space. And we know that the surface area is 108. So 108 equals 4xh plus x squared. Now I want to solve for h, so I need to get everything that's not h on the left side. So we have 108 minus x squared equals 4xh. And now I'm just going to divide by 4x. So we need a little bit more space. So what we have is 108 minus x squared over 4x equals h. So now let's take this expression for h and substitute it back up here. So we're going to have volume equals x squared, and then this expression times 108 minus x squared over 4x. Now we need to do some simplification. So we're going to get rid of some of these x terms. So this x term is going away, and one of those x terms is going away. So we have x times 108 minus x squared over 4. Now let's go ahead and multiply through. Volume equals 108 x minus x to the third over 4. So let's do one more simplification for differentiation purposes. We're going to separate this fraction out. 108 divided by 4 is 27x minus x to the third over 4. Now we can go ahead and differentiate this because we're all in terms of x and they're relatively simple operations. So dv dx, or we could have said just v prime, is 27 minus 3/4 x squared. So now we're looking for extrema, so we set this equal to 0. 0 equals 27 minus 3/4 x squared, and that will give us 3/4 x squared equals 27. And 27 divided by 3 is 9. 9 times 4 is 36. So x squared equals 36. And x is plus or minus 6. We don't need the negative 6, obviously, because that's not going to be a decent value here. We can't have a negative side length. So let's just assume that it's 6 for our critical number. And let's make sure that that's in fact a maximum. So let's put in a 5 and a 7. So evaluating our first derivative at 5, it's positive, and at 7, it's negative. So yes, in fact, that is a maximum. So now we know what our side length is. We know that our side length x value is 6. So we can find the other dimension just by substituting our x value in here. So 108 minus 6 squared over 4 times 6 gives us our h value. So this works out to 108 minus 36 is 72, divided by 4 times 6 is 24, which is 3. So that's our h. So now we know that our dimensions are 6, 6, and 3. And so now let's move on to another problem. In this problem, which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So let's go ahead and bring up a visualization of this. And we can see the graph of the function. This is the point 0, 2, and we have some point on the graph, xy, that we're trying to minimize the distance from 0, 2. So in this case, since we're talking about the distance between these 2 points, we're talking about the distance formula. So that's the function we're going to be optimizing. So here I've gone ahead and written down the distance formula. Distance is the difference of the x's squared plus the difference of the y's squared. Now our x values are going to be x minus 0 squared plus y minus 2 squared. The next step, x minus 0 is just x squared plus, well, this y brings up an issue because we don't want to have an equation in 2 variables to differentiate. So I want to replace this variable with something in terms of x. Well, it just so happens that our function itself, y equals 4 minus x squared, gives us an expression for y. So I'm going to substitute this value for y for this value. So down here, the y becomes 4 minus x squared minus 2. Now that's all we have to do is take 4 minus 2, and we have 2 minus x squared, quantity squared. In the next step, that's all I did, was expanded this binomial. And so this squared, this times 2, and this squared. That is the basic formula for expanding a quadratic binomial. So now I combine my terms. X squared minus 4x squared is negative 3x squared. We just copy down the x to the 4th and add our 4 in order. Now this is our optimization function, and we could go ahead and differentiate as is, but because radicals are 1 to 1, we only need to differentiate the discriminant, because this radical expression is going to be minimized when the radicand is minimized. So we're just going to take the derivative of the radicand just to simplify things. So we're going to say f of x is x to the 4th minus 3x squared plus 4, and then f prime of x becomes 4x to the 3rd minus 6x. Now we need only find the critical numbers of this, so 0 equals 4x to the 3rd minus 6x. Let's factor out some terms. 0 equals, we have a common 2x, and 2x squared minus 3. And so our x is 0, and we have 2x squared minus 3 equals 0. 2x squared equals 3. X squared equals 3 halves. X equals plus or minus the square root of 3 halves. So let's execute our first derivative test on these critical numbers. So when we evaluate our first derivative at -2, it's negative. At -1, it's positive. At 1, it's negative. And at 2, it's positive. So we know that our minimums occur at negative square root of 3 over 2 and at square root of 3 over 2. So our minimum points are negative square root of 3 over 2, 5 halves, and square root of 3 over 2, 5 halves. Of course, these values were derived by taking this value and substituting it into our original equation to find out what the y value is for that given x value. So there are our minimums. And now let's move on to the next problem.